Okay, so this is the first lesson for Chapter 7 for my grade 11 applied math students. You should be in this booklet here, Quadratics. And let's start by looking at some things visually. First of all, use the table of values to graph the following function. So that's the function y is equal to x squared. What does y equals x squared look like? Well, let's go back to kind of our grade 7 technique for graphing. Let's make a table of values. So if I'm making a table of values for this, I have to say, what is y when x is -3? Actually, I might just start the table not at the top. You know what the easiest number in this table to work with is? It's the 0. So if I were to put, hang on a sec, there we go. If I were to put 0 into this equation for x, so I have y is equal to 0 squared, well, 0 times itself is still 0. Let's go downward from there. What happens when I plug in x is 1? I get 1 squared. What happens when I plug in 2? I get 2 squared. What happens when I plug in 3? I get 3 squared. Now, oh, that's the ugliest 9 I've ever made. Let me make a better 9. 9. Now let's go the other way. Now careful with this. I think almost everybody here would have no problem with the actual arithmetic rule. What happens when you multiply a negative by itself? You get a positive. So you know that's going to be +1, +4, +9. But I see students write it down wrong all the time. I'm going to write it down wrong on purpose. Don't copy this. I'm going to plug in y equals x squared. X is -1. Do you get why that's wrong? I know the answer is supposed to be +1. That number isn't +1. You're probably going, but doesn't the square make the negative go away? Not like that, it doesn't. Like this, it does. Those are two different questions right there. The red one is y is equal to -1. What? I bet if you think back to grade 7, as early as grade 7, you probably had a math teacher who told you, anytime you substitute a number in for a variable, because they tell you what the variable's number is, put it in a bracket. But what if it doesn't need a bracket? Do it anyway. So if you had something like, oh, I don't know, 2x minus 3, and I tell you, hey, x is 4. Okay, great. 2 times 4 minus 3. That bracket wasn't really necessary. I could have just wrote 2x4, right? Like or I could have used a dot for multiply. But what if x was -4? See, there's some sense to writing the bracket now, because you don't want to confuse that by thinking it's 2 minus 4. It's definitely 2 times -4. And when you are dealing with a squared, let me erase all this. When you're dealing with an x squared, and I tell you that x is, say, -2, I do not want this, because that's wrong. You know what that is? That's -1 times x squared. This negative doesn't belong to the squared. It's its own coefficient. So these two numbers are not the same number. That is saying, I'd like the negative of 2 times 2, please, which is -4. This one is saying, I'd like to square everything in the bracket, and that includes the negative. So that's -2 times -2. That's a +4. These two numbers are not the same. Now, when I'm doing this, I have x squared, and tell me how much x squared is when x is -2. Which of these two situations is it? It's this one. So, did you not get a book? Oh, I'm sorry. Hang on. Let me get you a book. Oh, I left it by the front in case anybody came in late. Sorry about that. Okay, anyway, like I was saying, this situation is this. So this is wrong. Don't write that down. That's correct. That is +1. Y is equal to -2 squared. That is +4. So when I square all of the x values that are negative, I get positives. Okay, I think we're finally ready to start plotting some dots. Let's start with 0, 0. Let's go to the top of the chart now. -3, +9. -3, 1, 2, 3, +9. Negative 2, positive 4. Negative 2, positive 4. Negative 1, positive 1. Now let's keep going. We already did 0, 0. 1, 1. 2 over, 4 up. 3 over, 9 up. I think it's fair to say that we cannot connect all those dots with straight lines. This is definitely a curve, and that's why we call this quadratic and not linear. Linear means straight line. Any equation that has just x and y and no exponents other than 1 will be linear. As soon as you put a squared on one of your variables, you get a curve. And this kind of curve is called a parabolic curve or a parabola. But the kind of equation that makes a parabola, we call a quadratic equation. Now try to make yourself a nice curve. Don't make it too pointy. It's not the Pope's hat. It makes a nice curve at the bottom. Okay. Now we're going to do the same thing again, but for a slightly different quadratic equation. This one is x squared minus 4. So I still see some people drawing. I'll slow down a bit. Make me a nice curve. Here, you know what? I'll show you even. When I do this on Desmos, and I get y equals x squared. Check out how nice this curve is. I mean, this one's nicer than the one I made. This one's nice and smooth. But check it out. It's a smooth curve. Hey, when you zoom, no, another thing is, remember, we put the point 1, 1 on there. Here, let's put the point 1, 1 on there. 1, comma, 1. So when we put the point 1, 1 on there, a lot of people, when they're drawing this, they'll just connect those two dots with a straight line. Notice, zoom in, that's clearly not a straight line. Even when you zoom in on it a long way, it's still a curve. Hey, when you get a half for x, a half squared is a quarter. That should make sense to you. What's a half of a half? A quarter. So notice this path from 0, 0 to 1, 1 is totally not a straight line. It curves. At any scale, it's always a curve. No matter how much you zoom in, it'll always look like a curve. It's never straight. Let me go back home now. Okay, back to the second one now. Everybody had time to catch up on their drawing? All right, what's this one going to look like? Well, let's see. First of all, let's try, go away. Let's start with 0, 0 again, or when x is 0 again. If I plug in a 0 here, I'd get y is 0 squared minus 4. Well, 0 squared is still 0. 0 minus 4 is negative 4. So 0, negative 4. Okay? Let's work our way down again. What happens when x is 1? Y is equal to 1 squared minus 4. That's going to be negative 3. So 1 over, 1, 2, 3 down. Y is equal to 2 squared minus 4. That's going to be 0. So when x is 2, 1, 2, y is 0. Now what happens when x is 3? So y is equal to 3 squared minus 4. I better do this one in 2 steps. That's 9 minus 4, 5. So when x is 1, 2, 3, I go up to 5. So there's my first 4 points of my parabolic curve. Okay, let's try the negatives now. Remember, plug it in a bracket. Y is equal to negative 1 squared minus 4. Oh, we just had that conversation. The question was, why do we have to plug it in a bracket? Because these two things aren't the same number. They're not. They're not the same number. This is -1 times -1, which is 1, minus 4 is -3. That would be the negative of 1 times 1, which is -1, minus 1 is -5. They're not the same number. So, if that makes sense to you, we want this one, not that one. So this is y equals 1 minus 4, which is -3. Hey, do you see something happening here? 1 and -1 make the same number. Guess what about you could say about 2 and -2? They make the same number. And 3 and -3, they make the same number because this graph has a property that's very important in mathematics. The property is called symmetry. It is symmetrical around this point here. It's like if you drew a line right through that bottom point. I'll just make it a little dotted line here. It's like the left and right side of that dotted line is the exact mirror image of each other. It's the same shape it was on the graph above, so I'm just kind of curving this and curving it up and curving it up. Oh, that was ugly. Don't go down. It never goes downward. It's always getting bigger. There we go. Parabola. Give you a sec to catch up to the drawing, and then we'll go back to Desmos for a sec.
Are we allowed to use Desmos?
Yes. Once again, I think when we test Chapter 7, there'll be maybe a page or two where I don't let you have graphing technology, just to see if you understand some basics. But anything that involves calculating or graphing anything kind of difficult, for sure you get to use graphing technology. And if you don't want to use Desmos, TIs are really good at quadratics. They're actually even better than the shading stuff. The shading stuff got a little difficult on the TI because you had to, make sure you'd done a test already and knew which side to shade. Oh, quadratics, the TIs are just born for quadratics. Okay, so let me go back to the graph I drew, and let me show you again what we just did. We just, there we go. We just took that graph. Okay, I'm going to make that point go away. We don't need that point. We just took this graph, and we did this. We instead of graphing y equals x squared, we graphed y equals x squared minus 4. And, okay, let's put both of these graphs on the same grid. What do you notice about them? Well, they're exactly the same shape. It's like I picked up this red graph and I moved it down 4 units. There's people who go, well, it's not the same shape. These two graphs are going to cross somewhere. Actually, no, they don't. There's always space between them. Now, the space between them is getting smaller visually as I go kind of higher and higher. But you know what? There will always be a gap between them. They'll never cross. Let me go back to home here. So that is the same graph but moved down 4. Just for fun, what do you think would happen if instead of minus 4, this had been a plus 4? You think it's going to move up 4?
Yeah.
You're exactly right. Any idea how I'd make the graph shift to the left 4?
You put in negative x.
Yeah, instead of putting the plus 4 here, I actually put it as a minus 4 over here. That will shift it 4 units to the right. Now you might be thinking to yourself, hey, wait a minute. Why did a minus move to the right? Isn't the right the positive direction? Yeah, I can explain that to you though. Check this out. If you understand that making this, here, let me make that graph go away. If you understand that putting a plus 4 on here moves it up, notice that by algebra, I could take this plus 4 and move it to the other side of the equation. And if I had the equation y minus 4 equaled x squared, It's the exact same graph. In other words, a plus 4 on this side and a minus 4 on that side are the same thing. So you kind of have to think to yourself, well, if this value had been on the other side where y is, it'd be the same thing. Of course, it's being squared, so that makes it a little complicated. But basically, it's like an opposite rule. This 4 changes all my y values. It makes them go up 4. If I had that 4 on the same side as my y, it would kind of be an opposite rule. I think of minus 4 as going down. I think of plus 4 as going up. If the thing that I'm affecting, in other words, the y value, is on the opposite side of the equal sign, everything's cool. But when it's on the same side of the equal sign, I have to think oppositely. So this thing, let me get rid of that. This thing is the way, I think of this as my parent function, y equals x squared. What does this minus 4 do to it? It moves it 4 units to the right. If instead of plus 4, let's get rid of that guy. Control C, Control V. If instead of minus 4, this had been a plus 4, it would move it to the left. Because again, there's an opposite rule for this. All right, anyway, let's do some more drawing. First, a little bit of a note. What is a quadratic function? A quadratic function is a relation between two variables that involves squaring one of them, or squaring, I'm going to say, the input variable. So my example, the simplest example I can give you, is y equals x squared. What if I squared it the other way? What if I did x equals y squared? Can you do that? Yeah. But it looks like this. See, here's y equals, I'll go back to the page in a sec if you weren't quite done writing. If you graph y equals x squared, you get that. If you graph x equals y squared, oh, it goes that way. And who remembers from grade 10 what the rule is for a function? Is that thing a function? Yes, it's a quadratic function. Is that thing a function? No. Who remembers the rule from MAP? Why is this not a function? What did it fail? It failed the vertical line test. Do you remember that? If you can draw a vertical line through a graph or a relation between two variables and hit it twice, it's not a function anymore. So that's why when I say a quadratic function, I have to say it's the input variable. In other words, the input variable is the x. You like science class better than math class? What do you call the input variable in science class? Begins with an I. Somewhere Miss Piasecki has felt a chill go down her spine that you don't know this, or whoever you had for grade 10 science. Physics too. What do you call the input variable in physics? The x's are always called what? The I, N. The independent variable is x, and the dependent variable is y. Do you not remember that from science? I'm sure you did that in grade 8 and 9 too. No? You should have. All right, so more examples. They can look like that. They can look like, that's the simplest one I can give you. I can complicate it. I can put a number here. I guess I don't have to keep writing example. Obviously, these are all examples. I could put a number here. Ooh, you know what we haven't done yet? What if I put a number here? Ooh, what does that change about it? Okay, let's go back to my graph. Okay, I'll give you a sec to catch up to the writing. Let's go back to the graph. What does that change about the graph? So this minus 4 would move it down 4. This minus 4 would move it to the right 4. What would this 2 do to it? Interesting. Okay, let's see. All we can do is try it. If instead of, okay, let's get rid of that guy. If instead of y equals x squared, I have, well, let's just copy this again. Control C, Control V, there. What if instead of just 1x squared, I have 2x squared? What do you think is going to be different? Okay, check it out. Ready? 3, 2, 1. Oh.
Why is it thinner?
I don't know. Why is it thinner? Okay, pick a number. What's your favorite number? 0. That's a great number. When x is 0, y is 0 in the red one. In the blue one, when x is 0, oh, 2 times 0 is still 0. That's why 0, 0 is a point in both of them. But okay, let's go to our next point. Suppose we have the point 1, 1. Now 1, 1 is on the first graph. Oops. I meant to hit a 1, not the letter 0, or the letter O. 1, 1. There we go. That point's on the red graph, but where did this point come from? This point comes from the fact that if you let x be 1, 1 squared is 1, right? From our table of values back here, 1, 1's a point. But if we were to put 1 in for the input of x on this one, what would you get now? You'd get 2 times 1 times 1. So that point when x is 1 on this graph becomes 2. And then the point here, 2 became 4. I can't land right on it. There, oh, no, there we go. 2 became 4 on that one. What does 2 become on the blue one? Hint, what's twice 4? So it's like it goes up twice as fast. Hence, to you visually, it looks skinnier or narrower. What would I have to do? What if, well, let's change this too. Oh, this is fun. You get to do this with, put another letter here. I'm going to call this letter A, and then when you introduce a third variable, Desmos is smart enough to say, would you like this to be a slider? And you say, yes, please. And then you get to make a slider out of it. So what happens when A gets bigger and bigger and bigger and bigger and bigger? Ah! What if it got to be 1,000,000? It'd look like a straight line up and down, but there'd still be a gap. You just have to zoom in to find it. It's a curve no matter what. Okay, now, what if A, obviously when A is 1, it's just the same as the red one. What if A got smaller than 1?
Thinner in some sense.
0.1.
Wait, why did it expand again?
Well, again, start thinking about what's happening. When you plug in 1 here, and now this number in front of it's 0.1, you'd get 1 squared is 1, but what's 1 times 0.1?
0.1.
0.1. So instead of going up 1, it only goes up 0.1. When you plugged in a 2 here, 2 squared is 4, but if there's a 0.1 in front of that, what's 0.1 times 4? It'd be 0.4. So 2 becomes 0.4. And that's the way these things behave. What if I kept going? Well, obviously, if I hit 0, this thing's going to disappear. Meh. It's a line now. But what happens as I cross into negatives? It goes down. Let's zoom up here. I go back to home. Home. So look at this. I could do this all day. In fact, I can animate it. Yeah, it's fun. Desmos is fun. I could watch that all day. Okay, anyway. That's how parabolas behave. I guess now we can actually define parabola. The shape of a quadratic curve. Okay, I'm going to pause the video here and show the class something that I will put a link to on the blog once I find it. And I'm not going to go searching for it because I don't want any copyright strikes on my video. So I'm just going to pause the video here. And we're back. So I just showed a cute little video of something called Blob Jumping. I'll put a link to it in the blog so you can see it too. And basically the point is, any object that is launched, any projectile that is launched and thrown and flung and shot and launched into the air under gravity has to make a parabolic curve. Even bullets make parabolas. I know it's like, don't bullets travel in straight lines? No. Gravity wins that fight too eventually. If you have a big enough place to shoot at, you'll get a very wide parabola. So that A number we were just playing with would be decimal 0.00000, but it's still going to be an x squared after that. It's a parabola. So as you can imagine, if you're into the whole physics thing, math involving quadratics and parabolas is your bread and butter, because every object traveling under gravity is making a parabolic curve of some type. That's not the only places that these kinds of equations pop up, but it's one of the most common, and certainly one of the ones you'd see first in high school, because if you take high school physics, you're going to have to do math with parabolas. So there's those. Other places you see them that you already know. Anybody have a makeup mirror? A makeup mirror is a very tiny section of a parabolic curve. Now, it doesn't feel like a curve to you because they pour the glass flat over it, but the actual shiny part is a very smooth, very gentle, again, probably a very small, A is 0.000 something, but it's still a curve, and it's still a parabolic curve. So there we go. Quadratic equations make parabolic curves. Okay, check out this one. Y equals negative x squared minus x plus 6. Okay, I kind of want to start at 0 again, because 0 is nice and easy to work with. So this time I think I'm going to keep some scrap paper handy, which means I better erase all this. Oops, which means I better learn how my pen works. There we go. Okay, let me make that bigger too. There we go. Okay, so I'm going to make an equation here where x is 0. What's 0 squared? 0. What if I take negative 0? 0. What if I minus 0? 0, and then I add 6. Oh, okay, well, it's 6. So 0, 6. Let's make a point. 0, 6. Let's go down again. I think positives might be easier to work with than negatives. Y equals, okay, wait a minute. Negative 1 squared minus 1 plus 6. Mr. K, you told us to always put the negatives in a bracket. Well, I didn't this time. How come? Because the negative is in front of the x squared. It's part of the equation. Think, if you like, think of this as y equals negative 1 times x squared minus x plus 6. Hey, remember order of operations? What comes first, multiplying or exponents? Exponents does. So this is take an x number, square it, then times it by negative 1, then minus it again, and then add 6. So that's what I'm doing. Take the number 1, square it, it's 1. Make it negative, or times it by negative 1. So this is negative 1 minus 1 plus 6. Does everybody get that that's going to be 4? Try 2 yourself, or oops, I went the wrong way. Sorry, that way. Thank you. Try 2 yourself. See if you could do it without any calculator help. And I say without calculator help because I hate the way some calculators do this. If you have a fancy calculator, like my graphing one, like a TI, and there you go, and you just type in, oh, what's negative 2 squared? You know what? This calculator is smart enough to realize that negative's not being squared. That's the negative of 2 times 2. It's going to say negative 4. But if you have just kind of a regular calculator, one of those kinds of scientific calculators where whatever's on the screen, it does the operation of whatever you have there, and you put negative 2 on your screen and then you hit squared, it's going to think you want to square the negative. It's going to think you mean that when you might have meant this. Because again, those are 2 different numbers. They're not the same number. I hope I've made that point. Okay, so give yourself a second here. Without a calculator, try 2. And get ahead of me, try 3. And I see people punching calculators. Make me sad in the bottom of my heart. Come on, put the calculator down. You can do this. These are integers. We're not throwing decimals at you and stuff yet. You can do this without a calculator. Yes, you can. So let's see. Let me catch up to you now. Y is equal to the negative of 2 squared. If you want, it's like, but you said put it in a bracket. Okay, I will. Watch. Haha. It's in a bracket. The negative of 2 squared minus 2 plus 6. Does this bracket mean anything? It does not. But notice, B in BEDMAS stands for brackets. So do what's in the bracket. There's nothing to do in the bracket. It's just a 2. E stands for exponent. You're squaring the 2, and then you're timesing it by negative 1. Hey, what's that going to be? Is that what you got when you tried 2? It's 0. Okay, you know what? These things have symmetry. They have pattern. So let's see if we can figure out the pattern as we go here. What happens when you plug in 3? Y is equal to the negative of 3 squared minus negative 3 plus 6. Oh, sorry, minus, it's not negative 3. Minus 3 plus 6, sorry. So that's negative 9 minus 3 plus 6. So this is going to be, oh, hang on a sec, something went wrong here. I plugged in 3, hang on, negative 9, yeah, it looks like it is, yeah, you're right. It's going to be negative 6. That's negative 12 plus 6, yeah, you're right, it's negative 6. Okay, I'm kind of behind on my points. 1 becomes 4, so put the point 1, 4 down. 2 becomes 0, so 2 over 0 up. 3 over 6 down is there. Interesting. Now let's keep going. Let's try some negatives. Okay, I'm going to erase my scrap work so I've got more room to go again here. Using this thing came so much easier when I realized you could erase lots of things at once. So y equals, okay, so now I'm plugging in a negative 1 for x. But this original negative that I highlighted is still there. Okay, negatives of negatives of negatives. Isn't that exciting? Okay, what do you do with this? Well, what counts first? B is for brackets. There's nothing to do in the bracket. What's the next letter? E. Square negative 1. What do you get? But then I times it by a negative 1 because there is a negative 1 outside the bracket. So that's negative 1. Those negatives don't cancel because the exponent cancels this negative first. These two negatives cancel. What happens when you minus negative 1? Hey, this is interesting. When I plugged in 0, I got 6. When I plug in negative 1, I get 6 again. Interesting. Guess what we just found out? That thing has to turn around. That has to hit its highest point between negative 1 and 0 for x. Interesting. Guess what happens now? What's your prediction for what negative 2 is going to be? It's going to be 4. Can you see the pattern that's happening? Let's try it. Y is equal to the negative of negative 2 squared minus negative 2 plus 6. Negative 2 squared is 4, but there's a negative in front of it. Minus a negative is just like saying plus. Negative 4 plus 2 is negative 2. Negative 2 plus 6. Whoever guessed 4, you were exactly right. Guess what the next point has to be? You see the pattern? Let's see if it's right. Y is equal to the negative of negative 3 squared minus negative 3 plus 6. Negative 3 squared is 9, but I have a negative on it. Minus negative 3 is plus 3 plus 6. Negative 9 plus 9, 0. What? Am I doing the arithmetic too fast for you? Is your calculator going to help you that much with this arithmetic? Well, only if you really know how your calculator works.
What's the deductive reasoning?
What's the deductive reasoning? The deductive reason, that's an excellent question. The question was, people, I keep forgetting people who might watch this as a video aren't going to hear those questions from you guys. The question was, what's the deductive reasoning here? Well, deductively, I know these curves have symmetry. So it kind of should make sense that I see a pattern in the numbers. When I'm counting by the same thing when I'm putting in my inputs, I should see myself count by the same kind of thing in my outputs. So notice, the graph turns around somewhere. It has a maximum somewhere between -1 and 0. We'll learn in later classes how we figure out what that maximum is. It's somewhere higher than 6. I mean, it's not that much higher. This thing doesn't go up to some point. It's probably like a little bit higher than 6. I'll just estimate that it's there. But notice the points going down. -1 makes 4. Oh, hang on a sec. I just did that wrong. Yeah, there it is. Hang on. -1. -1 makes 6, sorry. 0 makes 6. -1 makes 6. -2 makes 4. That's what I was looking for. -2 makes 4. Notice that that has symmetry with that point. And then the next one is -3 makes 0. And then the last one, I'm expecting, you know what, I'm not even going to do the arithmetic. I know what it's going to be. It's going to be the same as that point. -6. Let's see if it shows the symmetry. -4, go down 5, 6. Looky there. Look at that beautiful symmetry. There's almost nothing more perfect in this world than parabolas. Parabolas are beautiful. Not that I don't like straight lines. Straight lines are nice. But parabolas have a beauty, a perfection. Ah, parabola. There it is. Okay, let's do another one. Am I slow? Okay, well, I got to slow down for some people. We got some questions. Yes. Yes. Young man in the front row.
What are the cases that the quadratic function or the parabola has to be a...
Oh, you want to start talking about the quadratic formula already or something? No,
sorry.
no.
What are the cases for a parabola to be symmetric?
All parabolas have symmetry. What we see is that if you draw a straight line through its highest or lowest point, a straight vertical line, you get a mirror image on either side. So that's how I knew that this point here had to mirror over there and be right there. That's how I knew that this -4 would have to be a -6, because it's going to mirror the point that we got when x was 3.
Then if all parabolas are symmetrical,
Yep.
does that mean that every parabola's positives will equal to the negative side or something like that?
Well, yeah, but notice because this one doesn't have the vertex, I'm going to use the fancy word vertex. This parabola doesn't have its center point right on the y-axis. So notice these things don't kind of balance it exactly, right? Like in other words, -3 has a different y value than +3 does. Whereas if I look back on the parabola that was centered right on the x-axis or on the y-axis, -3 had the same value that 3 did. -2 had the same value that 2 did. Because this one kind of shifts over a little bit, I have to kind of look harder for the symmetry. Know what I mean? It doesn't exactly mirror on the x values, plus and minus. All right, like I said, let's do another one. All right. Y equals x squared minus 6x plus 5. Oh, this time we're just going to play with the positives. What happens when x is 0? 0 minus 0 plus 5. Okay, that's easy. That's the easiest one. Boy, just like last unit, I always tested with 0, 0 because it's easy to work with. Zeros are easy to plug into parabola formulas. 1's not that hard either. Y equals 1 squared minus 6 times 1 plus 5, which is 1 minus 6 plus 5. 1 minus 6 is -5. -5 plus 5, 0. Let's try 2. Y equals 2 squared minus 6 times 2 is 12 plus 5. 4 minus 12 plus 5. 4 minus 12 is -8. -8 plus 5, -3. All right. Now, I don't have matching points here, but I kind of do. Let's see. Let's try one more point and then see if we can figure out a pattern. What happens when y is 3? I get 3 squared minus 6 times 3 is 18 plus 5. 9 minus 18 plus 5. 9 minus 18 is -9. -9 plus 5. because I have 1 minus 6. No, it isn't. It's negative 5. 1 minus 6. You have $1 in the bank, you take out $6. What's in your bank account now? Negative 5. You owe the bank $5. Right? So this one here is 9 minus 18, which is negative 9. Negative 9 plus 5 is negative 4. Hey, look what's happening. It was high, it's getting low, it's getting lower. It's getting lower, but the rate at which it's getting lower is slowing down. Right? This goes down 5. This one goes down 3. This one goes down 1. What's going to happen when y is 4?
It'll be negative 3.
16 minus 24 plus 5. 16 minus 24 is negative 8.
Plus 5,
Negative 8 plus 5. Oh, I think I see the pattern back. What are you predicting for the next one?
It's a 0.
Should be a 0, shouldn't it? Let's double check. I need more scrap paper. Let's try it. 5. Y is equal to 5 squared minus 6 times 5 plus 5. That looks pretty 0 to me. What do you predict happens when you plug in a 6? It's going to be 5. All right, we haven't graphed any points yet. Let's graph some points. 0 over 5 up, right there. 1 over 0 up, right there. 2 over 3 down, right there. 3 over 4 down, right there. And then 5 over 0 down. Oh, wait a minute, I missed one. 4 over and 3 down again. There we go, I missed one. And then 6 over and 5 up. And look at that. Look at the beautiful symmetry. And then make me a parabola. And you should put arrows on it because it would go on forever. Parabola! All right. Now, I'm going to do this really, really quick for this next part. Do you need more time to catch up to the graph? Okay, I'll give you a sec to catch up to the graph. While that's happening, while people are catching up to drawing their graph here, I just wanted to point out kind of one more thing about this parabola. I'm going to do some counting. I'm going to count like my favorite Sesame Street character, that vampire guy. My wife asked me one time, she said, what's your favorite vampire? Because hers is that sparkly guy from Twilight. So I said, mine's the Count from Sesame Street. She says, Sesame Street, he doesn't count. And I said, yes, he does. Okay, so if I can't have children's puppet show vampires, my favorite vampire is probably Blade. Come on, how cool is Blade? All right, anyway. All right, here we go. Ready? Start here. This is a very good starting point. It's like where the graph turns around. It's got a name. It's called a vertex. Okay, focus. How much do you have to go up when you move over 1? If I go 1 that way, how much do I go to get to this point up? Well, 1. If I go over 2, how much do I have to go up? 4. If I go over 3, how much do I have to go up? We better count at this point. 1, 2, 3, 4, 5, 6, 7, 8. Do you see a relationship between those numbers? 1 over, 1 up. 2 over, 4 up. 3 over, 9 up. What if I went 7 over? How much would I go up? 49. Why? Because those are squares, and that's what this graph is based on. It's based on squares. So you can remember that. You can always kind of figure out the shape of these things by just counting. All right. I said we're going to do this part really quick because we already looked at this with Desmos a little bit. What's the effect of a in y equals ax squared plus bx plus c? Well, if a is greater than 0, which is, of course, means positive, then my parabola does this. It's upwards. If a is less than 0, let's take a look. A was a positive 1, it goes up. Look back here. Aha! A was a negative 1, I highlighted it even. And it went down. So if a is less than 0, which is negative, it goes downwards. And then we played with it on Desmos a little, and we found out if a is greater than 1 or less than negative 1, I get narrower. I don't even know if that's a word, narrower?
In what instance does A
Want me to go back to my, you want me to go back to my animation? It's probably still rolling.
be positive or negative at the same time?
No, I said or.
No matter if it's going up or down, it's getting narrower.
Thank you. No matter whether it's going up or down, it's getting skinnier. See, here it is. Bigger than 1, skinnier. And if I go to this side and I'm less than 1, skinnier. But when I'm between 1 and negative 1, what's the word I'm going to go for here? If A is between negative 1 and 1, so it's like a half or negative a half or a third or negative a third or 0.7 or negative 0.7. If I'm between 1 and negative 1,
Your straight line.
it gets wider. And it looks like a wide smile. So there's the A effect. One last example. I'll give you a sec to catch up to me, but feel free to look ahead. How many X-intercepts can a quadratic have? Now, what does X-intercept mean again? We learned this back in linear stuff. It means it's where it hits the X-axis. It could have 2, but does it have to have 2? It could be 0, or it could be 1. How could it be 0? No, it's not. It's how many. How many X-intercepts can a quadratic function have? How many times could it cross the X-axis? Okay, use our graphing calculator. So I'm going to say let's use Desmos. So everybody, if you've got your phone handy and you can get to Desmos on your phone. If you have a TI and you want to use a TI, I'll show you how that looks in the TI. But let's do the first one. So the first one is y equals, and you can type on the keypad for those of you using a phone, y equals x, and here's how you square. Squared minus 6x plus 8. And as you can see, that parabola has a vertex at -3, 1. Or sorry, let me say that again. 3, -1. So I'm going to draw that. So 3, -1. There's its point. Oh, this is going to make you very happy. It's a nice small grid again. Those of you watching this at home, there's been many complaints from one person in particular about how small the grids are on some of our notebook pages. But we won't name names. And we hit the x-intercept at 4, 0, and 2, 0. So I'm going to go back to my graph, and I'm going to graph those. 4, 0, and 2, 0. You know what? While I'm at it, you know what the other easy point to graph, again, almost always is? Hey, what happens when x is 0? You get 8. So 10, 9, 8. Parabola. Do, 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 do. Parabola. There we go. Okay, so there's the first one. Just using technology to let us make a sketch. Oh, and I promised you the TI. The TI is really easy. Go to your TI calculator and make sure that all your stat plots are off. So let's see, go to stat plot. Yep, good, we're off. And clear everything. Make sure you go to your window, go to zoom and just say standard. So zoom 6, so that means you go from positive to -10. Get rid of any equations. I can see I must have been trying to graph a circle on here or something. Yes, I did. Ignore that. And then, okay, so now from here, what did we just graph? We just graphed x squared minus 6x plus 8. Boom! Graph that. And then you can just hit the trace feature, and you can just move your cursor along until you find out what the x and y intercepts are. Now it might not hit them exactly. You might have to estimate, or you can go to calculate. Oops, I said calculate zeros. Zeros are what you call x-intercepts. And then the left boundary, so let's see, let's go past it. Let's go, left boundary is over here. Enter. Right boundary, you got to pass by the x-intercept you're looking for. Then it's going to take a guess. The guess is always wrong. Ignore it. And there it is, 2, 0. The same point that we saw in Desmos by just hovering our mouse over it. So once again, the TI is kind of clumsy compared to Desmos. Desmos is the superior technology by a mile. All right, so there's the first one. Turn it off. What's the second one we got to graph? The second one we got to graph is y equals negative. And oh, I should be typing with this so that you can see how to do that. So let's see. A good question. Do you need to put the y? No, you don't, but that's kind of force of habit to me. You actually don't need to put the y. It'll assume that you mean y equals. Oh, and then of course I put it in the wrong place. Sorry. There. Y equals, and again, if you don't put the y equals, it doesn't matter. Negative x squared minus 6x minus 9. And look at that. Somebody was saying, how could you only have one x-intercept? Check it out. Can't the vertex be the x-intercept? It most certainly can. So let's graph that. So what was that again? That was negative 3, 0, and then just draw down. So negative 3, 0. And again, you want to draw down without having to do any calculations? Go 1 over, 1 down in both directions. Go 2 over, 1, 2, 3, 4 down. And then you could go down to 9, where you know the y-intercept is. And then there we go. Draw me a parabola. 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 So, 2 x-intercepts. Told you, I like the count. 0 x. No, sorry. The count just goofed up there. 1 x-intercept. People who have never seen Sesame Street have no idea what's going on right now. What do you think this one's going to do? This one's going to be 0. So what does that mean? Before we even graph it, what's it going to do? It's going to miss the x-axis. So let's see if that's true. Go to Desmos again and type in. Okay, make this one go away. You just click on this and then it just hides it for you. So again, you don't need the y equals, but it's kind of a habit for me. That's okay. So 2x squared plus 4x plus 3, and there it is. Your prediction was correct. It does not touch the x-axis. It does tell us the vertex. Desmos always tells us the vertex. On the TI, you have to ask for it to calculate. It tells us the vertex here is negative 1, 1. So that's what I'm going to graph. I'm going to go to my graph and go negative 1, 1. And I know it has a y-intercept of 1, 2, 3. And then I know by symmetry there'd be another point over there. And that's good enough. Draw me the parabola. And say the conclusion. 0 x-intercepts. Could it ever have 3 x-intercepts? No, because parabolas can't turn around again and come back.
How do I know?
Cubics can.
How did you know the other points in the parabola?
Good question. I guess I kind of glossed over that. So going backwards, let me start over. That was my vertex. I looked it up on Desmos. There it is. And I knew the y-intercept because the y-intercept is always this number here. It's the 3. So I went to my graph and I put the x-intercept down. Or sorry, the vertex, I put the vertex down. I put this x-intercept down, and then again, by symmetry, I know that there's an imaginary mirror line that goes down here. So then I just put this point over there because I know it has to look the same on either side of the mirror.
Does it have to be one point one number opposite.
Yep.
The
That's how
vertex.
mirror images work. Yep.
But then how did you know that was the zero intercept? Like,
Oh, because look, think about this. What happens to this equation, young man in the front? What happens to this equation when x is 0? And doesn't everything along the y-axis mean x is 0? Yeah. So plug in a 0 here, you get 2 times 0 plus 4 times 0 plus 3. So that's how I knew that this point had to be, 0, comma 3.
So then that would be the same with the 2x and 1x.
Yep.
Okay.
So there we go. All right, so that takes us to the end of the first lesson. That took me a little longer than I thought, but I was playing with Desmos and blob jumping, all that kind of stuff. Okay, so I'll stop the video there so people who missed this lesson can still catch up on it.